Good morning. Let us continue our lectures devoted to properties of stochastically differentiate functionals from the Wiener process. Let me recall you that we constructed in general case for functionals from the Gaussian white noise in the separable Hilbert, real separable Hilbert space, such a new variable like a stochastic derivative and extended or Skorokhod stochastic integral. And last lectures, we decided to see what is the realization of these notions when the white noise is generated by the standard Wiener process. Up to this moment, we know that if we have standard Wiener process, for example, in the interval 0, 1, and we have the random variable alpha, which is square integrate and measure with respect to sigma fields generated by this process, then alpha can be uniquely represented as a sum of the following kind: sum from n equal 0 to infinity. Here is n multiple integral from deterministic kernel the kernel is supposed to be symmetric and square integrate on the corresponding power of the interval 0, 1. The integral of such kind must be defined because we have the Wiener process, so it is defined as follows: the integral from 0 to 1 and a n t1 tn dw t1 dw tn is equal to n factorial multiply with the integral of a simplex delta n delta n a dw t1 dw tn. In this simplex coordinates t1 tn are ordered in non-decreasing order, so this integral can be easily defined as Ito or Wiener integral subsequently, and we just decided to produce such a formal definition, very similar to the well-known fact that if the function is symmetric, then usually the back integral with respect to cube is equal to n factorial integrals with respect to simplex. But this notation is very convenient because if we use such expansion, then it inherits all properties which we mentioned for general case of the functionals from arbitrary Gaussian white noise. Here we have expectation of alpha equal to a0, and expectation of alpha square is equal to the sum from n equals 0 to infinity. Here is n factorial, and then integral from 0 to an square dt1 dtn. In terms of this E2-winner expansion, one can define stochastic derivative of the random variable alpha in case if this derivative exists as a random function d alpha t is a sum from n equal 0 to infinity n multiply here is n minus 1 type integral a n t t1 tn minus 1 dw dw t1 dw tn minus 1. We discussed it already that stochastic derivative satisfy good property, has good properties like usual derivative, and actually can be defined, as we have seen, as a closure in two sense of a usual derivative on the functional space. So one can apply, for example, chain rule or rule of differentiation of the product. Also, we defined the conjugated operator to stochastic derivative. Namely, we discuss the operator V, which is equal D star, and is acting on the space of random functions to the space of random value. And if X is a random function such that X of t has a E2-winner expansion like following. Here you see that kernels depend on the additional coordinate t, dw t1, so dw tn. Then it occurs that in case of existence, the extended Skorokhod stochastic integral from x has a form p of x is equal to sum from n equals 0 to infinity. Here is n plus 1 multiple Wiener integral, but from the special kernel. This lambda bn means symmetrization of bn with respect to all coordinates all coordinates t1, tn. So now it depends symmetrically on n plus 1 parameters dw t1, dw tn plus 1. Okay, so now we have such an expression, and we finished our previous lecture with some examples of stochastic derivatives of special functionals. Namely, we discussed stochastic derivatives of integral and the stochastic derivative of solution to stochastic differential equation. The main idea of our consideration was the following. We are supposing that because the stochastic derivative and extended or Skorokhod stochastic integral are related in this way, that maybe this relation can be seen as an integration by part formula. It is true. And usually, when we have some integration by part formula, this formula allows us to establish existence of the regular version of the generalized functions. Maybe you remember such trick from the course of generalized function or course of partial differential equation. So we will do more or less the same. We're supposed to use stochastic derivatives of random variables in order to get the existence of the density of probability law of this random variables. Before to do this, we need some properties of extended stochastic integral. And last time I promised the one to solve the one intriguing question. Namely, the question was the following. Here you see a purely algebraic definition of the extended stochastic integral. And one can ask, we already have a very nice and well-developed theory of stochastic integral. How it is related to this construction? And this is the first question which we will solve today. So let us consider such function xt, and suppose that this function is adapted to the flow of the sigma field generated by the linear process. So let us introduce the sigma field ft, which is sigma field generated by the values of fs up to the moment t. And I will suppose that for all t which belong 0, 1, we have the following: the restriction x on the interval 0 t is measured with respect to, is measured with respect to t. So I suppose that x is square integrable random function such that then the statement is following. The statement is following. Here. X belongs to the domain of definition of E, and E of X is the usual integral xt d. So in a word, Ex is integral from x with respect to w. This is a statement of our theorem, and let's prove it. Of course, to prove this statement, we will detailize properties of the Ito-Wiener expansion of the function x, because the extended stochastic integral was defined via this expansion. So we have, let me recall you that we have the following expansion. And then we have the extended stochastic integral as a random variable with the symmetric kernels obtained from Bn. Let me consider firstly the case when x has a very simple expansion, namely it contains only one summand here. So I will suppose, firstly, this is the first step, that x has just following expansion. It is one term from the general series. And before to discuss the symmetrization of this form of this kernel, I want to use the property that x is adapted to the flow ft. So let us recall that x is adapted to flow I'm claiming that this leads to the following relation: B A T B1 Tn is equal to 0 when maximum of T1 Tn is greater than. This is my statement. So I'm claiming that the following relation holds. How one can check it? To prove that some function is equal to 0 on the subset of our cube, 0, 1 in n power, it is enough to check that all integrals with respect from this function with respect to subsets of which lies outside which lies outside of the domain where T1 Tn is less than T is equal to 0. Namely, what we need to check, we need to check the following: that if delta is a subset of a set of such vectors T1 Tn that maximum of T1 Tn is greater than T, then the integral with respect to delta, our bn dt1 dn dt1 dtn is equal to 0. So when we prove this, we will get the desired relation for the function bn. How we can do this? I will take a special form of the set deltas. Why I can do this? Maybe you remember that suppose this is, for example, two-dimensional case. I will draw it just a simple picture for explanation. This is T. This is our domain where we have to take some set delta. And of course, you understand that this set can be taken as some break. Yeah? It is enough to take delta as such of the such form. So I will take delta as the following. Due to symmetry, I just consider one coordinate here. So I will suppose that delta has a form, some interval AB multiply delta prime, where AB is a subset from T1 and delta prime is arbitrary. Delta prime is just a subset of 0, 1 in n minus 1 power. This is set where all other coordinates live. So after we choose this in the following way, then see what happens. I can try to consider the functional from Wiener process related to this set. Namely, if I will suppose that delta prime is symmetric, let me recall that we consider B symmetric with respect to all coordinates, symmetric. Then one can try to calculate the following expectation of the product of our random variable from 0 to n, Bn, T1, and so Tn, dWT1, dWTn, multiply on the integral with respect to delta prime, dWT2, dWTn, and multiply on the integral from A to B, dWT what we will have here? Now, what we will have here? We have here integration with respect to n minus 1 linear process plus 1. So we have here n linear processes, and here we have n linear processes. So exactly as we did in the abstract case, one can check that from one side, it is equal to n factorial multiplied with the following. Here will be integral from a to b, and integral with respect to theta prime, bn dt1 dtn. From other side, it is 0. Other side, it is 0. Why I am claiming this? I have to say that delta prime is just of such form dn. Why it is this? Because this integral does not depend on the Wiener process up to the moment t. We take interval AB after the time. So this increment of the Wiener process is independent from both of these variables together, and our x by condition. This also due to this relation. From this, one can check that this is equal to 0. And from here, since delta is arbitrary, one can get the following. One can get the following, that our bn t1 tn is equal to 0 if maximum, if for example t1 is greater than t, but t2 tn is lesser. This is not all. These are not all the cases, but in order to get more general case, we have now suppose that we have two indices t1, t2, which are greater than t, and other one t3, tn are less than t. Then you again have considered now the random variables of the kind. Now we have the integral with respect to AB, CD, dwt1, dwt2, t2, and then multiply on the integral of n minus 2 multiplicity and do exactly the same. And since A, B, and CD are taken from the interval t to 1, then this again is independent, and we can continue this process and get finally that in this case we also have the same equality. Then take t1, t2, t3 greater than t, and so on. Repeating this procedure, one can get that we have desired property, namely that that our kernel bn is equal to 0 if maximum of t1 Dn is greater than from this reason, I can write it as follows: xt now is equal to integral from 0 to t n time, and here is bn t t1 tn dw t1 dw tn. This is very convenient because now I can rewrite it as integration with respect to simplex. Let me recall you that we have here only formal expression, which was defined as n factorial due to the symmetricity with respect to these coordinates, multiplied on the integral over simplex delta nt because of this t, and here is the same kernel t t1 tn dw1 dw tn. Then when we have such an expression, let me recall that this is simply the iterated Wiener or Ito integral already. So let me write this integral in more long formula, but more convenient for Ito integration. So it is exactly the following. It is equal to n factorial multiply the integral from 0 to t. Here is integral from 0 to tn, and so on, integral from 0 to t2, h b and t, t1, tn, dw, t1. This is the first integral up to t2. Then dw, t2. It will be the second integral here up to t3, and so on. dw, tn, and this is the last integral from 0 to t. And here there are no any abstract constructions. This is just repeating Ito integral. We know what is it. And now maybe everybody understands that in order to have the Ito integrals from our xt, I just need to add another integration with respect to Wiener process, and I can do this because this is all the Ito construction, so everything is adapted and so on. So now it is understandable that I can integrate xt with respect to Wiener process and get the following. The integral from 0 to 1 xt dwt will be equal just another one integral, sign of integral. Here is n factorial, here is 0, 1, here is integral 0 to n, and so on, 0 t 2 bn t t1 tn dw t1 dw tn dwt. Yes, here is and now we have something very similar to the Ito Wiener expansion, this random variable, which I recall you is Ito integral. Let me even write this. Ito integral. What is the difference between the canonical Ito-linear expansion and this integral? The difference, of course, is the following. This is not symmetric function. Yeah? This is not symmetric function because, as you remember, the variable t plays here a special rule, namely, if the maxima of this T1, Tn is greater than T, then this kernel is zero. So there are no any symmetry here. It is symmetric just under permutation of T1, Tn. But of course, we can try to do symmetrization. Yeah. Let us consider symmetrization of Bn. Let me write it somewhere. So let us check what is lambda Bn T1 Tn plus 1. What is it? Of course, it is simply sum. Probably one can imagine the general construction of symmetrization. Yeah, some overall permutation of these coordinates from Bn. But now we don't need the general construction because we already have kernels which is symmetric with respect to last and coordinates. So in order to have symmetrization, we just have to put this biggest coordinate on this place, this place, this place, this place, and so on. Okay? So it is like 1 over n plus 1. This is number of the choice of the maximal coordinates. Okay? And here is Bn from T. Excuse me, here is the sum. Sum from J equal 1 and plus 1. This is just number of the biggest coordinate, the largest coordinate. Yeah. Here is Bn, Tj, and then T1, Tn plus 1. But just remember that Tj is already here, so it is missed here. Here there are no number j. It is also already here. Yeah. So this is a symmetrization, and one can try to change our notations and put here symmetrization. Let me emphasize that on this set, I just recall you that this is a set like following. This is the biggest coordinate. So I can say that this is already symmetrization. Due to the property, let me recall you, that Bn T1 Tn is equal to 0 when maximum T1 Tn is greater than T. Due to this property, this function is already equal to this sum. Yeah, because all other summands in this domain, all other summands will be equal to 0. So up to this multiplier, we have here symmetrization. We only don't have this multiplier in the denominator. So put it in the numerator. And then I can continue. And write finally that it is equal to n plus 1 factorial, because we need additional n plus 1 factorial integral over theta n plus 1 symmetrization of lambda beta n dn dw. So now one can go back to the definition of the extended or Skorokhod stochastic integral and realize that it is exactly this one. So I will continue. With the following, it will be equal the integral because of this factorial and symmetricity of this kernel 0, 1 and plus 1 lambda bn dw1 dw dn plus 1. Now let us consider the beginning and the end of the formula, and you will see that this is exactly the Skorokhod integral for the end of function x. So we have that in this case they are equal. Now, of course, one has to check general case, but I think that I will leave general case for the sum for you as an exercise, because we can use the fact that this is a closed operator and this operator is continuous with respect to the square norm of the function x. So we proved our theorem, and now we know that for adapted functions, Ito integral is a Skorokhod integral. So one can expect that maybe the name extended stochastic integral is reasonable, because this integral operator E is in some sense extension of the Ito integral. But to say this, we need the examples of non-adapted random functions which are integrate, which is in the sense of Skorokhod. Actually, we have some examples in the finite dimensional case. Maybe you remember that in finite dimensional case we discovered that extended stochastic integral is in some sense differential operator of the first order on the space of sufficiently smooth functions, and it looks like a divergence plus some additional. So maybe one can expect that in general, we also can build examples of the random functions which are in the domain of extended stochastic integral using some condition on the stochastic derivative. It is true, and I propose to go in such way. We will get general sufficient condition for random function to be in the domain of extended integral through its stochastic derivative. And after this, we will automatically have a lot of examples of non-adapted to the Wiener's law random functions, which still are in the domain of extended stochastic integral. So this is a way how we will proceed. And let us do this and look for sufficient conditions of the existence of sufficient condition of existence of Skorokhod integral. To find this condition, let me recall you that we defined one stochastic derivative and discussed more or less detailing its properties, and just mentioned that in the same way one can define second stochastic derivative, third stochastic derivative, and so on, exactly as it was done in the usual real analysis, when we detailedly studied the first derivative and then say, okay, in the same way we can define highest derivative, and they have similar properties maybe. But now we need a little bit detailedly consider the second stochastic derivative for a random function. So from now I will discuss the following case. I will consider xt, which is square integrate random function, and it's e to the next function. Here is integral from n 0 to infinity. Here is multi-kernel from 0 to 1, and dn t t1 dn dw d1 dw dn. And let me recall you that that this is a general case. So I have only the following condition: expectation of the integral xt squared t is less than infinity, but I have no any adaptiveness conditions. It's general case. From this point of view, we know that the kernel Dn is the following. Let me recall you that now we have the following property of the kernel. Bn t excuse me, Bn to L2 0 1 in n plus 1. And it is symmetric only with respect to T1K. So now let me recall what is the stochastic derivative. dxt is a point S. So now I'm calculating stochastic derivative of the random function, random variable xt at the point S, because we remember that now stochastic derivative of the random variable is a random function. So from the general definition, we have the following expression for stochastic derivative. It is just now from n equals 0 to infinity. Here is n, here is integral from 0 to 1, n minus 1, bn ts t1 tn minus 1 dw t1 dw tn minus 1. And now we understand that maybe the stochastic derivative of our random function S can be considered as a random kernel with respect to these variables T and S. And please check that the expectation of this dxt s square, and here is integral from 0 to 1 dt ds is less than if, of course, the stochastic derivative exists. Yeah? So I can consider this random kernel is a random Hilbert-Schmidt operator. So let us write this. Dx is a random Hilbert-Schmidt operator on L2 0 1. Because we know from the functional analysis that all Hilbert-Schmidt operators on the space can be associated with kernels which are square integrated. By the way, this kernel is not symmetric. S is taken from the set of T1, Tn, and T is taken from the parameter set of our random function. So they have different role. Now, let me recall you another fact which you already know. We mentioned this fact when discussed the covariance operator of Gaussian measures in Hilbert space. That product of two Hilbert-Schmidt operators is a nuclear. So now I will use this fact in the following. Dx square. I just use the usual square is the nuclear operator. In L201 as a product of two Hilbert-Schmidt operators. Of course, random. I did not write this word random. It means that it has trace. It means that it has trace. Namely, if I take orthonormal basis En orthonormal basis in L201. One can imagine, for example, some trigonometric basis in L201. Then the following sum is well defined. Trace dx square, which is equal to sum from n equal 1 to infinity. Here is dx square en. And this sum does absolutely converge and does not depend on the choice of basis. This is a trace. And finally, we have such a nice statement. Finally, we have such a nice statement. the following theorem holds. If there exists d of x, then x belongs to the domain of the extended stochastic integral, and we have the following nice relationship. Expectation of ex is equal to expectation square. Expectation of the norm of x square. I just recall you that x is square integral function. So norm of x square is an integral from 0 to 1 x squared t dt plus trace of dx square. So this is a sufficient condition for function, for random function to be Skorokhod integrate, and this is the precise expression for the norm of the extended of Skorokhod stochastic integral for such random function. We will prove this condition, but before we will prove it, let me make some very interesting remark. Let us pay attention again to this definition of the trace. See, dx was not a symmetric operator. Due to this, its square, which is nuclear operator, as we discussed, is not positively defined. Yeah? This is not dx multiplied on dx absolute. This is simply dx squared. It is not positively defined operator. One can roughly say that it is arbitrary nuclear operator, but arbitrary nuclear operator can have negative trace. Then look here. It can happen that we will have here 0. Yes. Then E of x will have will be 0. So we will see that there are non-trivial random functions such that the extended stochastic integral is 0. This is a difference between Ito theory and Skorokhod theory. Yeah, we have not only extension, but extension with very ridiculous properties. Okay, next lecture we will consider the theorem and continue with the existence of the density for stochastically differential random variables. For today, that's all. Thank you for attention. Maybe somebody have questions or comments, please. Okay. If there are no questions, thank you for attention and see you next week. Bye.